Hello and good afternoon, CTS265 Section 840 students for the Fall 2016 semester at Anne Arundel Community College. This is the CCNP route course, and this afternoon's video tutorial is going to be our introduction into OSPF, or the Open Shortest Path First Dynamic Routing Protocol. Now, recall from your CCNA studies that the OSPF routing protocol is a link state routing protocol as opposed to a distance vector protocol like EIGRP. And so the link state routing protocols are going to behave a little differently than distance vector protocols, and one of the major differences is the link state database that needs to be the same for all routers in the same area. Right? So remember that as we go to work through this discovery activity. And again, this discovery activity is sort of an introduction into OSPF. So let's take a look at what we've got here. We've got Area 0, Area 1, and Area 2. So we have a multi-area OSPF deployment here. And Router 1 is our area border router, or ABR. And the definition of an ABR is a router that has an interface in Area 0, which is commonly referred to as the backbone area, and at least one interface in another non-Area 0 area. Right? So Router 1 clearly meets the requirement. It has its interface in Area 0, and then it has at least one or more interfaces in a non-Area 0 area. In other words, Area 1 and Area 2. It has these two interfaces. Now remember, an interface can only be a member of a single area. So we can't have Ethernet 00 being a member of Area 2 and Area 1, and maybe if there was an Area 51 over here, can't do it. The interface can only belong to a single area. So let's go ahead and dive in. We're going to configure OSPF on the WAN and LAN interfaces on Router 2 as well as Router 3. So let's go ahead and get in here from user exec to privilege exec into global config. Do show IP interface brief. And it looks like we've got a loopback interface as well as a serial interface. And so enabling OSPF is very similar to enabling EIGRP, where we would say router EIGRP1, where here we're simply going to say router OSPF. And now this is not an autonomous system number. And so this is one of the distinctions that I want to make sure that I clear up, or I shouldn't say clear up, but make clear. And that is that when we configured EIGRP, we said router EIGRP, and if we were using name mode or if we were using classic mode, we had to define at some point in that process the autonomous system number, because for EIGRP, it's the autonomous system number that dictates whether or not two routers are in the same domain, EIGRP domain. So with OSPF, it's a little different. With OSPF, it's the area designator on the interface in question that determines whether or not two OSPF routers are in the same area. And so the process ID, when you do your reading, you'll see that it says that the process ID is locally significant. And that is true in our scope. Where the process ID is not locally significant is sort of an advanced scenario where we would be talking about an MPLS layer 3 VPN scenario, where the PE and CE are pairing with OSPF and the process ID is not the same. So for our purposes, it is locally significant for the scenarios that will be working, but keep in mind that that is not a universally true statement, that it does start to carry some significance just outside the scope of our class. So we simply say router OSPF2. If I do a question mark, you can see we've got access here to a whole host of OSPF commands. So one of the things that we could do for router 2 is I could say router ID 2.2.2.2, or if I didn't manually define it, it would take the highest IP'd loopback address if there's no loopback addresses, then it would have taken the highest IP numbered up interface, and then after that, we would need to locally define. If we didn't have any IPv4 interfaces, we would need to define it. So now we need to enable the OSPF process on the two interfaces in question. So do show IP interface brief. And we're talking about serial 00 and loopback 0. Now there's two ways we can do this. I'm going to mix and match here as we go along. So I'm in the OSPF configuration section. So all I need to say is network 172.16.12.0, and this is going to be a /30 0000.3, and then what area do I want any interface in that subnet on this router to be in? So if we go back and take a look at the diagram, you can see that there's that /30, and this is the interface that we are going to be starting the OSPF process on right here, router 2's interface right there. So we are in area 1. So let's go ahead and say area 1. And if the HQ router, what's the name of that router there? I'm sorry, router 1. If router 1 was configured, then we should have seen an adjacency come up. We may have to do some configuration work on router 1. Now, I could put the network statement in again. However, there's a much simpler way to do things, is to simply go under the interface in question and say IP OSPF, and then we simply put down 2, that's the process ID, and then we put in our area 1. So IP OSPF 2, area 1. And so now the loopback address is also being advertised into OSPF. And the same thing when you come into OSPF, if I were to say router OSPF 2, we can say passive interface default, and then I could say no passive interface loopback 0 and no passive interface serial 00. And then that's going to bring that neighbor adjacency back. So if I were to say do show IP OSPF neighbors, you can see right now we don't have any neighbors. The neighbor is down, or it says it's detached, right? So we're going to go ahead and we're going to fix that here in a second. But one of the other things to notice is just like we say show IP EIGRP interfaces, I can say show IP OSPF interfaces. Now let's take a look at this output here, because it is chock full of a number of important pieces of information. So we can see from the output that we've got loopback 0. It shows us the area that loopback 0 is a member of. It says it's attached via an interface enable, and the text does a good job of calling this out. You can see it's attached how? A network statement. So here we use the network statement, whereas here we said IP OSPF 2 area 1. Now the network type shows up as loopback with a cost of 1. That's the metric. On the serial interface, it tells us that it is non-broadcast with a cost of 64. Again, it's a serial interface, and we've got the area 1 designator as well. And you can see here the cost for the two links is enabled. Now, one of the differences that you'll notice, or I shouldn't say one of the differences, but when we go to configure a broadcast segment, like an Ethernet segment, you can see here the hello interval, because it is a non-broadcast NBMA network, the hello interval is going to be 30, and the dead interval is going to be 120. And so what that means is every 30 seconds a hello message is going to get generated. If I miss 4 consecutive hello messages, which means we reach that dead time, then what's going to end up happening is the adjacency will go down. Now remember, when we're talking about non-broadcast multi-access, or NBMA, that OSPF is going to treat NBMA networks just like Ethernet, right? Or just like a broadcast type. Even though it says non-broadcast, it's going to treat it just like a broadcast type. And typically you're going to see those in like a hub and spoke environment, or where you're running frame relay, where you're running frame relay, ATM. And if we look here at the drawing, you can see we are kind of hub and spoke, right? So this would be our hub with area 0 behind the hub. and we've got area 1 and area 2 hanging off the same hub. But again, this is our branch spoke site and our branch spoke site here. All right, let's continue on. So we've got area 1 taken care of here on router 3. And then you can see, there we go. We went from loading to full. So now if I say do show IP OSPF Neighbor, you can see there that we are in the full state and that the DR is router 1. And that is the router ID of router 1. You can see the dead timer is counting down. And there is the IP address of the peer, and this is the local interface out which we have that adjacency. So let's pull up router 3, go from user exec into privilege exec into global config, and the same thing, router OSPF 3, right? Again, that's a locally significant value, so I could use a different process ID on every single router if I needed to. And we're going to do the same thing, do show IP interface brief, and we're going to say network, and we'll do it backwards this time, 192.168.3.0, and this should be a /24, and this is in area 2. And then I'm going to go into interface Ethernet 00 and say IP OSPF 3 area 2. And it's that second command there that should then bring up the adjacency, and there you can see we went from loading to full. So do show IP interface, or not IP interface brief, I apologize, IP OSPF neighbors. You can see there's my single neighbor, again the DR, which is router 1, and then do show IP OSPF interfaces. And there's the two interfaces. If I wanted to, I could also say router OSPF 3, passive interface default, no passive interface serial 00. No passive interface, it was serial, is that correct? Oh, Ethernet 00, sorry about that. Ethernet 00. So there we go. And we'll leave the loopback address as passive because we're not going to be establishing any adjacencies out the loopback interfaces. All right, so let's also do the router ID. So I'm going to say router ID is going to be 3.3.3.3. Now, watch what happens here. When I type in the router ID 3.3.3.3, you can see that we get a message telling us I need to restart the process. And the reason for this is that it's the OSPF router ID that identifies this router node in the link state database graph. So in other words, as other routers are trying to solve and recurse to the quickest route, the shortest path, each router is being identified by the router ID. And so that's why this value is so critical and why it's going to force me to clear the OSPF process, because what's going to take place behind the scenes is OSPF is going to be generating some link state information that it's going to then re-advertise to everyone in the same area so that everybody knows that I am now router ID 3.3.3.3. If I were to say do show IP protocols, do show IP protocols, you would see that the router ID right now is 192.168.3.1. And this makes perfect sense because that is in fact the loopback address IP. And so it's being used as my router ID. Now, just like the router ID for EIGRP, it's going to be a 32-bit value in dotted decimal notation. That, just like EIGRP, it certainly looks like an IP address. It is not. It's not being used as an IP address. It's simply a 32-bit value that takes the form of a dotted decimal IPv4 address. But it's not being used. So when we use 1.1.1.1 or 2.2.2.2 or 3.3.3.3, none of those are going to be used as IPs. In fact, to prove that, if I were to say, right now on this router, if I was to say, let's get the cursor back here, do ping 2.2.2.2, you can see I have no reachability, even though that is the router ID for router 2. Because again, it's a router ID. It is not being used as an IP address. It just shares the same format as an IP address. Okay, so, but I've got to clear the process in order for this to take place, so the change to take place. So I would say do clear IP OSPF proc. We're going to say yes, and you can see that the neighbors went down and that's going to have to reestablish because I have to send out link state updates that are going to notify everybody that, hey, listen, my router ID is no longer 192.168.3.1. It's changed. So if we come back and say do show IP protocols, what we see now is the router ID is 3.3.3.3. And so that's how you would change the router ID value on a router. And remember that this is not something that you want to undertake during the middle of the production day, because as you saw, it tore the adjacency down. It's going to flood an LSA type 1, right, which is a router LSA, with the new information about the router. All right, so let's go ahead and confirm that we have do show IP OSPF neighbors. So we do have our neighbors. Again, remember, neighbor ID, that 1.1.1.1, that is the router ID of the neighbor, the priority value. So this shows us with a priority value of 1, that is the default on OSPF network types, where we're going to have a DR BDR election. And there are two types. We've got the broadcast type and then the non-broadcast type, where we're going to have a DR BDR election, right? So when we look at the other types, so point-to-point, there is not going to be a DR BDR election. If we look at the point-to-multipoint, there is not going to be a DR BDR election. And so we'll cover those in more depth as we go along. Okay, so let's go ahead. If you're following along, we're going to jump down all the way to step 7. Because step 7 is going to be where we get onto router 5, who's down here, right? Kind of in area 0 all by himself, no external connectivity. Let's get into privilege exec, say show IP route OSPF. Because what we want to take notice of here is that the routing information that router 5 is learning, all of these network segments here, with the exception, I'll stop right before that last one. So these first 4 network prefixes, they're all OIA, which means OSPF inter area, and you can see the code right up here. And what that means is that this is routing information from another area, an area that this router does not reside in. And again, router 5 is in area 0, so he sees the information coming from excuse me, area 2 and 3 as inter-area information. The only prefix that router 5 sees as an intra area, which is with just the O for OSPF, is the 192.168.4. Everything else is coming from a different area. And so this kind of leads to the conversation that I opened up the tutorial with, that OSPF is link state. However, as soon as you introduce areas, right, multi-area OSPF, guess what? OSPF turns into a distance vector protocol, or I should say behaves, probably a better word there, behaves as a distance vector protocol, where router 5 only learns the information about area 1 that is going to be shared in from router 1. And the same thing, area 2, the information that router 1 has that he shares out with 4 and 5, that information, it's distance vector type behavior, because does router 5 see router 3 as the next hop? Well, let's go back and take a look. So if I clear the screen here and we go back to router 5, excuse me. And we see, and what prefixes are down there? The 192.168.3. So we look at the 192.168.3, which is right here. And it says via 172.16.145.1. Well, remember I said that every area has to have a link state database that's identical. Well, router 5 is only keeping a link state database for area 0. It's the job of the area border router, router 1, to then send in the information that it's learning from the other areas. Example is this prefix right here. So all that router 5 knows is I need to go to 172.16.145.1. If I come over here to router 1 and say show IP interface brief, that just happens to be the Ethernet 01 interface on router 1. So router 5 has no clue about where that route or where that prefix came from. It came from all the way down here on router 3, right? It's that loopback address right there. All router 5 knows, though, is that for me to get there, I come over here to router 1. And as long as I can recurse to router 1, router 1 is going to take care of everything else for me. So basically, it's distance vector behavior. It's just like distance vector, where router 3 advertises a route to router 1 in EIGRP. Router 1 is going to advertise it saying, hey, I'm the next hop. Because in EIGRP, the default behavior is that the neighbor is going to change the next hop value to himself, or in other words, quad zeros is what it looks like in EIGRP. But it just simply means next hop self, which means router 1, for all the information router 1 is passing to router 5 in EIGRP, he is saying, I'm the next hop. Well, we open this conversation about link state databases saying that inside the same area, all of the information needed to be the same, and it does. But this is the distance vector behavior of OSPF. As soon as you introduce multiple areas or any other area other than area 1, the area border router is now going to behave with distance vector type attributes, right? So again, you've got this prefix here that gets advertised up to router 1, and router 1 simply sends down a link state advertisement to router 5 telling router 5, yeah, just come to me and then I'll take care of everything else, which is very different than when router 4 advertises to router 1 and router 5 this loopback address. Here, the next hop is going to be router 4 because they're in the same area. And in this area, every router needs to know about the state of every link. And that is your link state database for that area. And again, think of router 1 as kind of like a gatekeeper for these other areas, for all of the areas really, because he's going to be sending type 3 LSAs, right? The inter-area LSAs into the different areas for the information that he is receiving as an area border router, because he's the gatekeeper of the information. But he's going to tell these guys over here the same thing, router 3 and router 2, all the information they learn. And if it's for this loopback address right here, it's not going to say, oh, your next hop is 172.16.145, whatever that IP address is right there. It's going to say, come to me, router 1, and I'll take care of it from there. So again, these guys out here, they have no clue what's going on in this area. The details of the area have been hidden from these other areas that are outside the backbone. So let's take a look at router 2 and let's see if that is the case. So here on router 2, we say do show IP route, the inner area information, and it's actually learning that network there. But if we look at the, what was it, 192.168.4.0, so if we look at 192.168.4.0, where's that? Here you go right here. So does it say that the next hop is router 4. No, the 12.1, that's router 1's IP. And the same thing for the 192.168.3.1. The next hop is router 1 saying, come to me. If I come over to router 3, we're going to see the same thing. So we say, do show IP route OSPF. And for both the .2 and the .4, 192.168.2 and 4, again, it's telling router 1 is basically giving a summary, right, to, and a summary, and it's not a summary in the sense of summarization, IP address summarization. It's giving a summary. It's giving summary information about the area. So it's not giving router 2 and 3. Router 1 is not giving router 2 and 3 all the area information from area 0. It's giving them just enough information to get to those prefixes. And really, the information they need is, how do we get to router 1? Because if I can get to router 1 says he knows how to get to those other prefixes. And that is distance vector. If I say, do show IP OSPF database, right? Very important command when we look at the summary LSAs, right? Summary link states for area 2. And you can see OSPF router process ID, the process ID is 3, the router ID is 3.3.3.3. So here are the link states, right? These are the area 2 link states. These are our type 1 LSAs, the router link state. That's a type 1 LSA. The type 2 LSA is going to be a network link state, but only when we've got a DR, BDR election taking place, and then we get our summary. And these are the type 3s. And take a look, and now you're going to see why the OSPF router ID, it does way more than loop prevention. It's all about, with the link state database and OSPF, it's all about how does a router recurse, how does it get to the advertising router so that the advertising router can then move that information along and route that information. So here's the 192.168.4 and the .2, and take a look. Who's the advertising router? Why doesn't it say router 4 or router 5? I think the 2.1 is at router 5. But again, all of these advertising router statements have been changed to router 1's OSPF router ID. And so these summary, again, not summarization in the terms of IP address summarization, where we're trying to consolidate the routing table, but summarization in terms of the database information out of area 0, in this case, out of area 0, right? And so that's what router 3 is being told, that if you need to go to that network, or this network, or that network, or that network, all you need to solve is, how do I get to 1.1.1.1? And then the recursion part is right here. Because then it's going to look and see, well, do I have a way to get to 1.1.1.1? And it's right there. I'm getting a type 1 router LSA. So yes, I absolutely know how to get there because I've got this type 1 LSA. And then it does the routing table lookup to see what the next hop is going to be, and off it goes. But again, that is sort of distance vector behavior, where router 3 in a different area only knows what router 1 is telling him about area 0. 3 has no idea what else is going on in area 0 or what area 0 looks like. Okay. So again, I want to make sure really, really clear on that, because OSPF can be just as tricky and just as difficult as EIGRP in some circumstances. So what we're going to do now is we're simply going to say show IP OSPF route, and let's get back in the window here. Let's go to router 5. So show IP OSPF route. And this actually gives us a breakdown. This is actually a really, really nice command. It tells me what backbone area information am I getting, and then it tells me what intra area, oh, I'm sorry, the intra area path list there, but then the inter area route list, right? So we get the intra area information, but then we get the inter area information. And these on router 5, this inter-area information would come in as a type 3 LSA. And so let's see if that's the case. Show IP OSPF database. And there they are. Here are my type 3 LSAs, the 12, the 13, the 2, and the 3. I've got the, where are we at here? There's the 3, there's the 2, there's the 12, and there's the 13, right? So those 4 type 3 LSAs are right there, and that's why they show up in the link state database as type 3 as well. So now let's go on to router 3 here, and we're going to kick off a debug. And this is where we're going to see that when we talk about the election process between the DR and the BDR, and the election process, the way it works, is that the BDR is actually elected first, and we're going to see that here. So let's go ahead and get out of there and say debug IP OSPF adjacency. And if we still debug right, IP OSPF adjacency. Debug IP OSPF. We're having a problem spelling today. Adjacency. So there we go. So we've got debugging on. So clear IP OSPF proc. We'll say yes. And as you can see, we get an exchange of information here in the process. But let's go back up here to the top and take a look. Who gets elected first? The DR or the BDR? It's elect BDR. So it's the backup designated router that is actually elected first before the designated router gets elected. Right? The designated router gets elected second in that process, but it gives us a good idea here as to there's the DR BDR election. Then we come down to the database descriptor packets. Right? And remember, you've got those 5 different packet types that you're dealing with in OSPF. You've got your hello packets that are maintaining the adjacency. You've got your database descriptor packets, and these are the packets that are passing the information back and forth about the link state database. Keeps your link state database up to date and in sync. You've got a link state request, right, which is like, hey, I need to synchronize. I want to synchronize my database. I think I said link state update already, and then we've got the link state ACK, the acknowledgement, which is guaranteeing that guaranteed delivery, making sure that the information is being received as it should be. Okay. So that's the output of the information there. And let's move on now past that setup. And we're going to step down to step number 10 is where we're at now. So I'm going to come over here to router 1. And we're going to say show IP OSPF database. Right? And you can see router 1's got all kinds of information. The database here is going to be much bigger. And why? Exactly, because router 1 is an area border router. So router 1 has interfaces in 3 different OSPF areas, which means that router 1 needs to have a full copy of the link state database for each of those 3 areas, because he is the gatekeeper as an area border router at those area boundaries. And so that's why the information that you're seeing here is going to be far more comprehensive than information we see on just a member router, like, for example, router 4. We come over to router 4 and we say show IP OSPF database, and that's it. That's all router 4 has. Again, here is the type 3 summary LSA information. Again, you can clearly see advertising router, and there's the OSPF router ID again, which is why that OSPF router ID is so critical to OSPF and the ability to solve the shortest path and to figure out where do I recurse to and how do I get there. Okay, so now we're going to take a look on router 5, and we're actually going to shut down. It looks like we're talking about, and let me make sure I'm clear about this here. So step 11, we're going to shut down an interface, but I believe we're shutting the interface down. We're talking about the DR BDR. So let's Yeah, actually, well, I'm rolling back to step 10 here. So on router 1, if I were to say show IP OSPF Neighbor, you can see that the DR between 1, 4, and 5 is router 5 is currently the DR here. You can see that router 1 is probably the DR on that link, but the BDR is router 2 and router 3, and router 4 is the BDR. So yeah, and that's what they've got us doing here. So if I look on router 4 and I say show IP OSPF Neighbor, yep, you can see that router 1 is the DR, or I'm sorry, router 5 is the DR, and the druther. So remember, in terms of the way OSPF adjacencies are formed, and you'll see why this is full and that shows full, right? Because again, router 4 is the BDR, and so we have the DR, and think of the DR, think of it as just a pseudo node in a BDR. It's a pseudo node that's out there that's going to be responsible for the synchronizing of all of the information in an area. And so here we go. We've got the DR, who is router 5. The BDR is router 4, and router 1 is just a DR other with router 4. Because what ends up happening is, from an adjacency standpoint, it's going to be, the way that it's going to end up happening here is everybody is going to be adjacent to the DR and the BDR, right? So if I had another router over here, say router 9, okay, these guys would not form a full adjacency. They would form a druther status or a DR other status, because you don't want to have a full mesh of adjacencies forming fully, because then you've got that n times n minus 1 divided by 2 scenario that you run into, which is, it can exponentially grow to an unmanageable number of peerings, right, or adjacencies with other routers. So from an adjacency perspective, 1 is in a druther status with 4. 4 is the BDR, and 5 is the DR. If we had this other router here, he would be fully adjacent here, but this would be druther. So they know about each other, right? They know about each other, but they're not fully adjacent. It would show two-way if we added another router in there. And so that's something to take note of, and we'll talk about the all SPF routers address, as well as the all DR BDR routers address, the 224.0.0.5 and 0.0.6. Okay, so what we're going to do now is we're going to force the election, or I shouldn't say force the election. We're going to start the election process, but it's the BDR who's going to become the DR. It won't be the DR other router. So, and again, and this is for speed of convergence, to make sure that the link state updates that are being sent around, that get sent to the DR and then down to all of the routers, that happens in a very, very quick fashion. Okay, so let's do this. They're asking for, on router 5, to shut down Ethernet 0.0. And remember, router 5 right now is our designated router. So we're going to get into global config here, interface Ethernet 0.0, and we're going to say shut. And what this is going to do is, for router 1 and router 4, we're going to have an election as to who's going to be the new DR. And so you can see it still shows 5 is the DR, because what's happening? So 5 is going to be the DR until when? You've got it. Until that dead time. So now we're on the countdown to extinction here. Until this adjacency goes away. And 2 seconds, and then it's gone. We should get a message, there we go, telling us that it went down. And now take a look. So from router 4's perspective, router 1, who was DR other, is now the BDR. So who's the DR now? Well, let's come over to router 1. And we can see that on the segment we're talking about, router 4, who was the BDR, is now the DR. And that's how the election process goes, right? Hello, and again, so it's already, once the topology is converged and you have your DR and your BDR, the only election that's going to be taking place is for the BDR. Because whoever wins that BDR election is going to sit there and wait until the DR fails, and then that's when the DR, or when the BDR, steps in and takes over as the DR immediately. So the only election that's going on is, well, who's going to be the new BDR in case this DR goes down and fails. So now what we're going to do is on router 1, we're going to artificially manipulate the priority value. We're going to try to increase the priority value. Remember, the IP OSPF priority values are 0 to 255. 0 means that they're not going to participate in the DR-BDR election process at all, ever. 255 gives you the best chance to become the DR. And so let's go ahead and get into interface Ethernet 01, where we're going to say IP OSPF priority, and we're going to go ahead and set the priority to, they show 100 here. Because again, what's that default priority value? Exactly, it's 1. So we set the priority to 100. Now, the big question is, when I say, and what is router 1 right now? Router 1 is the BDR, I believe. Let's make sure. Yeah, router 1 is the BDR, right? Router 1 is the BDR. So on router 4, if I come over here to router 4 and I say clear IP OSPF proc, we're going to have another election, but let's see what happens. Show IP OSPF Neighbor. Router 4 now sees router 1 because, again, the hello packets needed to be exchanged. And router 1 is now our DR. If I were to say show IP OSPF interface Ethernet 01. And I thought that was show IP interface brief. Maybe that was router 1? 00, sorry. So show IP OSPF interface Ethernet 00. And if you come here, you can actually see it tells you right now. Transmit delay, 1 second, state. What is the state of this interface? Right? BDR. This is a backup designated router interface, which means if I went over to router 1 and said, and this is our Ethernet, do show IP interface Ethernet, do show IP OSPF, do show IP OSPF interface Ethernet 01. And this is where we see that, yes, we are in fact the DR of this link. Now, this section that they talk about the OSPF behavior with NBMA networks and hub and spoke. And if we take a look, that's really what we've got, right? We have a hub and spoke. And by hub and spoke, I mean we don't have, everything is not fully meshed. This is a partial mesh with a hub router and spokes hanging off of it. If everything was fully meshed and we were all in one area, it would not be hub and spoke, but it is here. And so this note here that they give you where it says, by default, OSPF treats NBMA topology just like any other broadcast environment. Partial mesh physical topology does not provide multi-access capability. A neighbor cannot be auto-discovered by default in an NBMA network. And so frame relay, so this is our NBMA network here. This is not. Area 2 is not an NBMA network. The frame relay network is our NBMA network. And this, right, this would be a multi-access broadcast segment here. It's Ethernet. This is going over frame relay for its layer 2, right? Ethernet is layer 2 in area 0. Our layer 2 over in area 1 is frame relay. So the hub must act as the DR and the spokes should never be candidates, and it also states that you need to configure the neighbors manually. But if we come in here to router 1, say do show run section OSPF, you can see that that is what they're saying. Because if I were to say, and let me make sure I get the right interface here, Ethernet 01. So if I were to say, and we've already said it, you can see here that the network type is broadcast. Because again, that very first statement, by default, OSPF treats NBMA networks where your layer 2 is frame relay, X25, ATM, DMVPN with a multi-point GRE interface is also looked at as NBMA. But by default, that's going to be a broadcast network type. And you can see it right there when we look at the interface. The interface is telling us, hey, I'm a broadcast network type. So, okay. Now, the text is telling us, right? This lab is telling us that we need to use a static statement. And that is certainly one way to handle or to approach this issue, right? Where, hey, I need to statically define the neighbor because it's not going to happen on its own. Another way that we can deal with this is we could turn around and change the network type on that interface. Just like with those loopback addresses, right? When I say do show IP route, OSPF, let's say OSPF. When I'm seeing the loopback interfaces, right? That loopback interface right there, it shows up as a /32. Do you see that? We're learning that the 192.168.3, and where is that? It's way down here. So here's that 192.168.3, but is it a /32? If I come down here and I say show run int loopback 0, no, it's a /24. But why is router 1 getting it as a /32? And this is where the network type comes into play. If I go back down to router 3 and I say show IP OSPF interface loopback 0, it takes it as a loopback type. And again, it's clearly a /24, right? There's not a typo here. So if I wanted this to show up with the correct subnet mask, all I would have to do is change IP OSPF network type to point-to-point. Right? And then it will no longer advertise that as a /32. If I come back over here, let's take a look now. Now what is it? Exactly. It advertises out. So the I guess what I'm trying to say here is all of those different OSPF network types all play a very important role. So what I could do, instead of statically defining the neighbor, is I could change that interface to point-to-multipoint. And so if we come back here and take a look at the diagram, let's take a look and see what the serial interface is. Do show IP, IP OSPF interface serial 00, is it? Yeah. So here, non-broadcast, right? So I could change the network types to be point-to-multipoint, and in fact you can even mix point-to-point and point-to-multipoint if you wanted to. You just have to adjust the hello timers, right, to make sure that the timers match. So let's do that. Let's see what happens. Let's see if I'm telling you the truth here, and we're going to mix and match here. So here on router serial 00 interface, or router 2 interface serial 00, let's see IP OSPF network type point-to-point. Right? Now that's going to take the adjacency down, right? Because I've just basically broken OSPF, changing the network type from one that was working to one that is not working now. Then I'm going to come here to router 1, and we're going to go into the router OSPF, I believe it's 1. Hold on one second here. Do show run section OSPF. It is. Router OSPF 1, I'm going to say no neighbor 172. So I'm going to remove this static configuration that was required before. I'm going to get into interface, and which interface is it that goes out there? It's serial 20, okay. 00 and 20. So on interface serial 20, you can see we've got all this information here. IP OSPF network type point-to-multipoint. And let's see, does that bring things up? But there's one thing that we have to change still. And what do you think it is? So now when I say do show IP OSPF interface serial 20, it is a point-to-multipoint interface, but what are the hello and dead timers? right? The hello time is 30, the dead is 120. If I come over here to router 2, and we now say do show IP OSPF interface, what was it, serial 00, you can see it's point-to-point, but what are my timer values? Exactly. The hello and the dead are 10 and 40. So we need to make that change as well. IP OSPF, where are we at here? Hello interval. And we're going to change the hello interval to match the other side. So now when we look, the hello and the dead timers and take a look at that. We now have an adjacency back. So the network types in OSPF, and we saw the non-broadcast. We saw the fact that it treated the frame relay on the router 1 side as broadcast, demanding that we have to statically define that neighbor. So there is an alternative here. You can change the network type on an interface. I could have made both sides point-to-multipoint, or I could have made both sides point-to-point. And then we took it to the extreme. You can mix and match as long as, and the question as to whether you can mix and match is all based off of, will a DR BDR be elected? If there's a DR BDR, those network types can be mixed and matched. If there's not a DR and a BDR, those network types cannot be mixed and matched. So broadcast and non-broadcast, those can be mixed and matched. Point-to-point and point-to-multipoint, they can be mixed and matched. And we just need to make sure, again, that our timer values are correct. So if I were to say now, do show IP OSPF Neighbor. All right, so is there a DR BDR election for point-to-point or point-to-multipoint? No. So then I can mix and match them, and all I have to do is I change my hello interval so that my timer values match in the OSPF hello packets that are going back and forth every 30 seconds, and we're good to go, right? And so that's one way to overcome the NBMA network. And so now we're down to step 15, where it's talking about the IP OSPF priority here. Oh, okay, on router 4 and router 5, it wants us to basically turn off or to remove them from participating in the DR BDR election. So IP OSPF priority is going to be 0 on Ethernet 00, and then on router 5 we're going to do the same thing. We're going to come over here, interface Ethernet 00, and we're going to say IP OSPF priority 0. So now what this means is router 4 and router 5 in area 0 will no longer participate in the DR BDR election process. And so the priority value is going to change to 0. Because on links where there is no DR BDR election, the value for the priority defaults to 0. On links where there is a DR BDR election, the default value is 1. All right. So we made that change. And let's go ahead, let's step over to router 1 here and say, do show IP OSPF Neighbor. And you can see router 4, and actually the interface on 5, I believe, is still down. We should probably do show IP interface brief. Did we administratively? We did. Ethernet 00, and let's say no shut and bring him back up. And so there will be no DR BDR election that 5 or 4 will be participating in. Show IP OSPF Neighbor. IP OSPF Neighbor. And there we go. What's our priority value now? And this is what we were talking about right here. You can see that router 5, since there is no BDR now, there's no backup designated router. We are single threaded here, single point of failure with router 1 as the designated router. And so 4 and 5, while they will become fully adjacent with the DR, and if there was a BDR, the BDR, what do we see now? Now we see that 4 and 5 are in the two-way state, and they are DR other. Again, because adjacencies are formed only with the DR and the BDR. And it's the DR and BDR's responsibility to ensure that that link state information is being synchronized throughout the area. Whereas other routers, they're simply adjacent with the DR and the BDR. They are not adjacent with each other. And the fact that neither of these, router 4 or 5, that neither of those routers is participating in that DR-BDR election, it clearly indicates to us that they will go into a two-way druther state. If I came over to router 4 and said the same thing, do show IP OSPF Neighbor, you can see with router 5, it is a two-way druther relationship. Okay? All right, so what we're going to wrap up with here is the MTU size on router 3, and I have actually been bitten by this in the past, in my past. So this is one that's near and dear to my heart. The MTU must match between the links. So on router 3, we're going to go to interface Ethernet 00. I'm going to say IP MTU 1400. Right? So now we've obviously dropped it down below the 1500 default. And on the other side, if I'm looking at router 3 here in the diagram, on the other side, I didn't make any change here to router 1. So now we have a mismatch in the MTU. So let's go ahead and kick off the debug IP OSPF adjacency. So we're debugging that, and let's say clear IP OSPF proc. We'll say yes. And in this debug, what we're going to start to see, and there you go. I mean, boy, that was pretty quick. You all. So what we see right away is neighbor has larger interface MTU, right? And we know that the MTU on that interface is 1500. You can see received database descriptor from 1 with a sequence number that's being tracked, options flag, the length, MTU 1500, state is EX start. And in fact, that is the state that if we said show IP OSPF neighbors, that is the state that it's going to bounce between, right? So it's going to go to EX start, but it's never going to get past EX start, okay? Because the MTUs do not match. And so obviously, one of the things that we could do is we're in that exchange start state. If I were to say show IP OSPF neighbor, we should see that it's stuck in the EX start still. If I went over to router, let's see, router 1, do show IP OSPF neighbor, you can see exchange BDR. It's stuck in the EX, the exchange start state. So what I could do to fix that is come over here to router 1, interface Ethernet, and what's that out, 00, and I could say IP MTU 1400. So now the MTU values match, and take a look. Loading to full, loading done. So we have our adjacency back. Now the same is true of the timer values, and we actually already saw this when I changed the network type to point-to-point and point-to-multipoint. Two network types where no DR-BDR election takes place. But both of those network types have different hello and dead timer values. And so what ended up happening was I made the change, nothing happened. It wasn't until I went on to, I think it was router 2, and made the change to the hello time that then you get 4 times that as your dead interval auto-magically, and then the adjacency came back up. And so they're asking us to go ahead and tweak, as a sort of a final thing here, is to tweak the hello and the hold time intervals between router 1 and router 2. So let's do that. And that interface is going to be serial 20. So let's go interface serial 20. And we're going to say IP OSPF hello interval. And we saw this already. We're going to set it to 8. Now, when I set it to 8, and actually, this is going to break the adjacency because this is where we did the point-to-point. But we're going to power through it here. So IP OSPF hello interval 8, IP OSPF, and again, by default, if I were to say do show IP interface or IP OSPF interface serial 20, right, you can see that auto-magically it forces the dead time to be 4 times the hello interval, which is why they have us say IP OSPF dead interval 30, right? So I'm changing both values. Now, do show IP OSPF neighbor. We had that countdown up to 120 right here, right? So you see it's clearly we're on the countdown to extinction here. It's at 52. It was all the way up to 120 seconds, right? And so you can see it's clearly coming down here. And there's going to be no end in sight. right? So 38. It's just going to continue to drop on that link between router 1 and router 2. Because the hello packets are going back and forth right now, and both routers are seeing, hey, your hello and dead interval don't match mine. If that's the case with OSPF, the adjacency is not going to function. You can see we're down to 17, 16. All right, so we're going to go ahead and let this time out, and then we're going to sort it out by simply matching those values over on the router 2 side. So 3, 2, 1, done, and we should get a message here telling us, there we go. We'll come back over to router 2, and that's okay, because on router 2, all I need to say is interface serial, is it 0, 0? Yeah, 0, 0. IP OSPF hello interval is going to be 8, and the IP OSPF dead timer, or dead interval, is going to be 30. And now those values match again. Even though the network types don't, it's okay because you can mix and match those if they both don't do a DR-BDR election, right? Okay, so now our adjacency is back up. The values match, so we can see the MTU value as well as the hello interval and the dead timer. All of those values need to match. The final check is they do show IP OSPF neighbor detail. And this gives us a little additional information here. When we see that neighbor 111, the state is full. We've had 6 state changes. You can see the neighbor priority. Our DR and BDR, right? It's nobody. And we know that because why? Exactly, we're using a network type that does not support the election of a DR and a BDR. And we're doing that in place of a static neighbor definition. And again, both ways are correct. You could do it both ways. I just want to make sure that I show you that not only can you change the network type, but that you can mix and match those OSPF network types. All right, well, that is going to wrap up our introduction into OSPF v2, which is for IPv4 configuration, and we're in discovery activity number 9. All right, have a great weekend. I'll see you on Monday night.